This video is going to be a quick introduction to error correcting codes, and in order to introduce the idea, I'd first like to recall what happened at the end of the video on error detecting codes. So there, we had a code C, which was as follows. So it consisted of three 5-bit strings, like so. And what we saw is that this is two error detecting. And what I mean by that is that if someone transmits a message to you over some sort of noisy channel where there might be up to 2 bits changed per code word, then we could at least tell that something had gone wrong if we received a message that was slightly garbled. And so the example given there was if you receive this message, 11000, then you look at this right here and you say, yes, indeed, that is an error. But so you know it's an error because the code word is not in C. But the problem is you don't know how that error happened. It could have come from two valid code words. Either the person intended to send you 5 zeros and the first 2 bits got messed up, or they might have intended to send you 4 ones and a 0, and it's these 2 bits that got messed up. So we can't correct the error when we're using this code. Okay, but now suppose that we were working on a sort of slightly better channel, that there wasn't going to be so much chance of errors being introduced, and now there's at most one error per code word. Well, then what happens? What's going to be different? So now, suppose, so at most, one error per code word. Well, then you wouldn't find yourself in a situation like this. That's going to be sort of the moral of the story. So to illustrate, so if we get a corrupted message, say like this, 1 2 3 4 0, and then the same second term, but now only one bit has gone wrong in the error term, then we actually know what the intended message was. So we know this was supposed to be all zeros, because there are no two code words in the code C that are 2 apart, in the sense that if you change a single bit in one, you can get to this mistaken code word. Or if you change a single bit in the other, you can get to this mistaken code word. In fact, it's not unique to this error. Any string that's 5 long, which is 1 away from a valid code word, we're going to be able to correct it. So let me write that. In fact, so any single bit error can be corrected. And there's a sort of mathematical reason why that works. And the reason was something that we observed about this code last time. So the reason why is that the distance between any two code words, so the Hamming distance, that's the number of bits you have to change to get from one to the other, it's bigger than or equal to 3 for any pair of elements st in this code. So that means that if you start with a word in this code and then you measure that the distance from s to some other string t is 1, then t must have come from s with one error. So t arose from s with one error. So that means if you see a string t in a message which didn't come from C, it must be an error, and it must have come from S. Okay, but now we can generalize this to the concept of K correcting instead of just being able to correct one error. So this code C would then be called one error correcting, and in general, So in general, C is K error correcting if you never have this problem of ambiguity when trying to resolve detected errors up to K errors per code word. If, so the distance is always bigger than or equal to 2K plus 1 for every pair of elements S, T, and C. And so the way that you should be thinking of this is, so K errors in one code word can be fixed. So it is fixable. All right, let's do an example of a famous error correcting code. The example is going to be denoted by H. And what it's going to be is all 7-bit strings that consist of bits. I'm going to label them B1, B2, B3, B4, B5, B6, B7, and they have to satisfy a system of equations. So satisfying. So the system is a little bit complicated, so bear with me here. So B1 plus B3 plus B5 plus B7 equals 0. B2 plus B3 plus B6 plus B7 equals 0. B4 plus B5 plus B6 plus B7 equals 0. And this is all mod 2. All right, so that means if you sort of started looking for solutions to this system of equations amongst all 7-bit strings of ones and zeros, you would be able to start filling in the set. You would find it contains things like this, or like this, and so on. Okay, this is actually Hamming 7.4 code. A very famous error correcting code. And it's one error correcting. So that means what we need to show to convince ourselves that it's one error correcting is that any two solutions to this system of equations are at least 3 bits apart, meaning to get from one to the other, you have to make at least 3 changes amongst these bits, B1 to B7. So let me argue why that's true. So here's our goal. It's one error correcting. Okay, now why? What we'll do is suppose that S is an element of H. So it's a solution to the system of equations up there. Now let's change 1 bit in S. So change 1 bit. After that change, these equations are no longer satisfied by the new bits. So, for example, if you change B1, it appears only once in the first equation. The first equation fails. And here's why. The first equation was this. Oops, B7 equals 0. And this is mod 2. All right, so this quantity was even before we made the bit change. Now we change this right here, and if we change it from a 0 to a 1 or a 1 to a 0, that changes the overall parity of this expression on the left-hand side. So this equation is not going to hold anymore after you change 1 bit. Now, of course, this is just the example of changing B1, but it's the same if you change B2, B3, B4. You look for an equation that has that bit appearing only once, and then you see that having made the change, the equation fails to hold. So that means if you take an element of H and you change 1 bit, the result is something that's not in H anymore. Okay, now continue. Let's see what happens if you change 2 bits. Well, then the same thing happens, that the equations don't hold anymore. But why? It's a little bit more complicated. For an example, let's consider changing bit 3 and 7. So e.g. change B3 and B7. So what we're thinking of is we're taking an element S in this code H, we're changing 2 of the bits to be different. We want to show that this isn't in S anymore. So the reason that the equations don't hold anymore when you change 2 bits is, well, let's go back and take a look at them. So changing B3 and B7, let's look at the first equation right here. If we change B3 and B7, the parity of the expression on the left-hand side does not change. The 3 maybe changes from a 0 to a 1. The B7 changes from a 1 to a 0 or something like that. But with 2 changes, the parity works out to be the same. Now, this equation, it also has a B3 and a B7 in it. And changing both of those, again, doesn't change the parity of the equation. But now, the last equation, it only has one of the 2 terms in it, B7. So changing both of them only changes one term in this equation. So now the equation will fail because the parity of the expression on the left-hand side changes. So what we can see is that when we change B3 and B7, then equation 3 fails. And it works the same for any pair of bits. If you change a pair of bits, there will be some equations that hold because you've changed 2 bits in the same expression, but there will be some that fail because you only change 1 bit in the expression. So that means that if so the distance from S to T is 2, where T is the new string that you get by changing 2 bits, and S is the thing that started off in H, then that's going to imply that T is not in H. All right, and last, all I want to do is point out that there are elements in H that are 3 apart. So note the distance from the 2 elements I listed at the beginning. There, the distance there is 3. So that means that the distance S to T is bigger than or equal to 3 for all ST in H, with being equal to 3 a real possibility because here we see 2 elements that do have the distance between them equal to 3. And so that means that H is 1 error correcting.